Go Language Programming, Chapter 7, Unit 5. In this unit, we will cover data race cannot be avoided with wait group, and we will go over the mutual exclusion lock or mutex. Okay, so let's start. So basically, in this unit, we've been talking about using the wait group for synchronizing the your go routines. Okay, so it wait group only supports actually the synchronization for of the go routine, but it cannot really fix the race condition, between the go routines. The go routine still might be competing for some resource, and to go and either resource such as the some memory location that need to be able to read or write, and one go routine will access that first before the other go routine can access. So that means it cannot really, this wait group cannot really fix the race conditions. So the race conditions between go routine occurs when two or more go routines are competing for the same resource. Okay, so that's how the race conditions that we saw it in the previous example as well, that the go routines are trying to access that piece of memory at the same time. So in how does this happen? If you in as you can see it in this example, what we have at line number in example number 7-8, at line number 7, what we have is a global variable, global and a variable which is of type int, and then we of course create a wg variable of type wait group, and we create at line number 10 we create a function called count. Okay, that is the function called count, and very first thing at line number 11 we use a defer and use a call a done function from the wait group. Okay, so that means whenever this go routine will finish, it will decrement the counter, from the wait group. So in here we have a for loop, and in this for loop what we have is that we are incrementing this global variable. Okay, so now we are incrementing it how many times? We are incrementing it 10,000 times. Okay, this variable. Now when the multiple go routines try to modify this, okay, that means the race condition will occur. So this is a clear example of the race condition. If your code is like that. Now in the main, what we are doing is the same way as we did it in the previous examples. We are using a add function from the wait group, and telling it that, okay, passing two to this add function. That means we will have two go routines. Okay, and these are at line number 19 and 20. These are the two go routines that we have. Okay, so they both will start in the background, and then at line number 28 or 21, sorry, in this one we have a wait function. So this wait will have to wait until all go routines finish. Okay, that means this done within the body of the go routine will decrement 1, so so eventually it will become, the count will become to 0, and it won't be blocked anymore. So, but the whole idea is that these both go routines, which is calling, they will be running in the background, but within the go routine they both will compete for this memory. So the memory, global memory, is right here. This is just a one piece of memory. The name of the address might be 1000, and the memory name is global, which is right here. So, and in here, basically, we are incrementing. So when we did this line number 7, it automatically initialized to 0, right? Every variable in the go code automatically get initialized. In this case, since it's integer type, it will be initialized to 0. So then it will, the contents of this memory will be 0. This is the address of this memory. And basically, if the two go routines, so go routine 1 will access it, and then go routine 2 will access it at the same time, and they both are trying to modify the the this memory. And that's where the problem is. They are racing. Okay, so there is a race condition in here. Now, to avoid that, to find out if there is a race condition or not, you can just compile it with the dash race, and it will tell you, found one data race. So, it will find it, that data race. So now, to fix this issue, what can we do? So to fix this, in the next example, what we can do is basically use the locks. Okay, so let's look at the this let's look at this next example here. So mutual exclusion locks. So the sync package, as we saw, it provides the wait group, for synchronization, right? So sync package also provides the mutual exclusion locks with mutex. Okay, and that's what we will use it in this code, and that's how we can make sure that the resource, in this case, the resource is a global variable, that is basically locked, and it will only be accessed by one routine at a time. Okay, so serial, basically, we are looking at, since we are locking it, that means once the go routine is done, in the this piece of memory will be locked, and then once that routine is done, it will unlock it. Okay, so that's the whole concept behind it. So use mutex locks to fix the race condition. So that's how we fix that race condition. So mutex let you synchronize the data accessed by explicit locking. Okay, now, you can do this with the other method, with the channels, but we are not using the channels. To use the channels, we have to understand the channels, which we will see all that in unit 6. Okay, but right now we do not have any knowledge about the channels, what they are. So we are using this mutex to make sure that we lock the global variable. Okay, so sometimes it's more convenient to synchronize data access by explicit locking instead of using the channels. Okay, so it's really depending upon what kind of a logic that you're writing. You may end up using the channels. Okay, and sometimes it is much easier to use the things such as explicit locking. So let's look at this example 7-9. In this example, what we have is we import the package sync and import the package fmt, and then at line number 8 we have a global variable, okay, which will be initialized to 0, because that's what the Go compiler's responsibility is. Make sure that all the initializations are done, and then at line number 9 we are creating a variable wg of type wait group, okay, and then at line number 10 we have a w variable called w, which is of type mutex, okay, which is in the sync package, okay, and that will create the lock. W will be the lock. Now, within the body of the function count, all we have is, very first thing we do the defer on the done. That means, once it is done, decrement the count, and then, that means one go routine was utilized. And then within this for loop, we have a locking of that memory. So as you can see, w dot lock, okay, and then we modify this global variable, and then we unlock it. So if we really were looking at the previous drawing, we have this memory called global, and then it may be at some address location, and we have like two go routines that are accessing it, okay. So in this case we have one go routine at line number 23, and the other one is at line number 24. So you can say that go 1 and go 2, so these are the two go routines. Now only one of them will be able to go and modify the data in this memory, okay. They both cannot access it because of this lock, okay. So once first one, they both are running in the background. These both go routines are running in the background, and then they one of them will basically lock the memory for itself, modify it, and release the lock. This is releasing the lock, and then the second one will come and lock that same memory and release the lock. Since we have only two, that's why we have the add two in here, and then the decrement will occur because of this w done in the go routine, okay. And basically when it comes to line number 25, there won't be any more wait if the those background both go routines are finished with the task that they were working on, and then it will be able to print. And then if you run this code with the dash race switch, you would not see any races. It would not, because there are no races anymore because of these locks that we provided. Okay, so that's how this code will work. So this actually concludes Unit 5, Chapter 7.